One night in 1669, a German alchemist named Hennig Brandt was searching, as he did every night, for a way to make gold. For some time, Brandt had focused his research on urine. He was certain the golden stream held the key. Tonight, his patience would at last be rewarded. He had boiled the urine down to a concentrated paste. Now he subjected it to intense heat. Was this the legendary elixir that would turn lead into gold? Alas, it was not. Brandt had stumbled on the element phosphorus. This is how the discovery of elements began, with people trying to turn the substances of nature into something useful or valuable. But people are naturally curious, so as they worked with these materials, they began to wonder, what is this stuff? What is the world made of? Thousands of years ago, the Greeks proposed that the world is actually made of just 4 elements in combination: air, water, earth, and fire. Today we know that matter actually comes in more than 100 distinct varieties, neatly arranged in the periodic table of the elements. But for most of history, matter was a profound mystery, a 2,000-year detective story in which people across the world were trying to identify the elements and figure out how to use them. It's an amazing story, filled with unforgettable characters. In this series, you'll meet 7 extraordinary scientists whose findings drove the search for the elements. So join me as we retrace the steps of these chemical detectives as they struggle to solve the mystery of matter.
Eh bien, chers amis,
Major funding for The Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin.
One of the first big clues in solving the mystery of matter came from the discovery of the most immaterial stuff you can imagine: air. Of course, people have always known about air. They could feel the wind on their faces and see its powerful effects in storms. What they didn't know was that there's more than one kind of air. That changed in 1754 when a young Scottish medical student named Joseph Black set out to find a cure for kidney stones. He poured acid on this chalky substance and trapped the air that came out. To his surprise, this air didn't behave like air at all. It was heavier than ordinary air and promptly put out a flame. Black's discovery of fixed air, what we now call carbon dioxide, was a turning point in the history of science. People had long known about liquids and solids. Now, suddenly, they realized there was a third state of matter: gases, of which air is just one example. Over the next 20 years, the exploration of this new dimension would transform our understanding of matter. After Black's discovery, British scientists quickly identified 2 more new gases: hydrogen and nitrogen.
and then in the early 1770s, that astonishing investigator Joseph Priestley discovers all sorts of new airs.
Priestley was a minister by trade, but also an amateur scientist, what was then called a natural philosopher.
He was a great dabbler in things and was constantly getting obsessed with new fields.
Fields like the new science of gases.
Priestley's style of science is very interesting. He's a kind of inspired forager. He's basically messing around with different things to see what will happen. One of the things Priestley did was to pour acid on everything. He collected those bubbles, tested them thoroughly, and discovered all sorts of amazing properties.
By messing around in this way, Priestley discovered 9 new gases, more than anyone else in the world.
He was very much open to chance discoveries. He would stumble across things and he would follow his instincts, and he was always looking for these kind of fortuitous accidents.
One such accident happened in 1767 when Priestley was assigned a new congregation.
They put him in a house that happens to be right next to a brewery, and this turns out to be an incredible stroke of good luck. Priestley, being the constant investigator that he was, would kind of pop over and see what was going on at this brewery.
Just above the vats of beer, he discovered a haze of carbon dioxide bubbling up from the fermenting brew.
And he decided he wanted to do some experiments with their beer. Well, fortunately, they said yes.
Priestley found that if he simply poured water from one glass to another over the surface, the water would absorb the gas rising from the beer. The result was refreshingly bubbly. By 1772, he had invented a better method, generating carbon dioxide and injecting it directly into water.
In the space of 2 or 3 minutes, I can make a glass of exceedingly pleasant, sparkling water. You can't tell the difference between this and natural mineral water.
Priestley had invented carbonation. Remember that the next time you enjoy a soft drink. But with this act, he also set in motion a series of improbable events that would soon overturn our understanding of matter. It began when a British doctor suggested Priestley's windy water might be effective as a treatment for scurvy, a disease that plagued sailors on long sea voyages.
Scurvy was a huge problem for the military during that period, and so the idea that there was this potential solution that also happened to be a tasty beverage was appealing.
In 1772, Priestley addressed Britain's leading scientific organization, the Royal Society, and published a pamphlet describing his method for making soda water. He urged the British Navy to test the potential cure. Quick to pick up on this development was a defrocked Portuguese monk named João Jacinto de Magellan. A distant relative of the great Portuguese navigator, he was now serving as a French industrial spy.
Magellan is in the employ of the French government and is there basically scouting out the Royal Society for interesting items that he might be able to bring back to his bosses.
Sensing a potential military secret, Magellan alerted his handler back in France, Commerce Minister Jean-Charles Trudaine de Montigny.
Trudaine was interested in science, was a member of the French Royal Academy of Sciences, and immediately saw the possible value of this.
Trudaine, in turn, called on one of France's brightest young chemists, Antoine Laurent Lavoisier.
Et qui en est l'expéditeur?
Monsieur Trudin de Montigny.
Monsieur Trudin de Montigny.
Oui.
I know your precision when it comes to physics and chemistry, and I'm giving you a chance to be of service to your country. Please repeat these experiments and add your own observations. The value of these discoveries depends on our moving quickly. I hope you will not be long in getting this little work done.
Trudaine probably intended this politely phrased letter as an order rather than a request. Lavoisier really couldn't ignore it.
Though soda water would turn out to be useless against scurvy, this pointed suggestion by a government official acting on a tip from a Portuguese spy would set Lavoisier on the path toward his greatest discoveries. Born into a well-to-do Parisian family, Lavoisier had received a fine education and taken a degree in law. Now 28, he had joined a consortium that collected taxes for King Louis XV.
As a result, Lavoisier became a very wealthy man.
But his true passion was chemistry. Lavoisier spent 3 hours in his private laboratory before work every day and returned there after dinner, often accompanied by his young wife. Marie Ann Pultz was the daughter of one of Lavoisier's business partners.
Antoine?
Oui.
She was just 13 when they were married, but bright, outgoing, and mature beyond her years.
Lequel est-ce que tu préfères?
Marie Ann was virtually his collaborator. She knew English, learned chemistry, assisted Lavoisier in the laboratory. She was an extraordinary person. Had she lived in our own time, she probably would have become an outstanding scientist in her own right.
One of Marie Anne's most important roles was to create the diagrams and illustrations that accompanied her husband's published work.
Marie Lavoisier's drawings give us the eyes to look directly into Lavoisier's laboratory. We can see the people, we can see the devices, we can see the arrangements of those devices. We can understand what Lavoisier did so much better because of what Marie drew.
Spurred on by Trudaine, Lavoisier eagerly studied fresh translations of Black, Priestley, and other British chemists who had pioneered the study of airs.
The work of these previous experimenters merely hints at what's happening when air is taken up or released by different substances. I shall review all their work, repeat all their experiments, taking new precautions in order to develop a coherent theory. This subject, I believe, is destined to bring about a revolution in physics and chemistry.
What made this new science of air so revolutionary was that it threatened to topple the reigning theory of chemistry, a theory inspired by the mystery of fire. Most chemists believed fire was due to some fiery principle that was given up during combustion. And all our senses seem to confirm this idea. Heat, light, smoke, all are released as the fire burns. By the mid-1700s, this essence of fire had been given a name: phlogiston. Phlogiston was the foundation of chemistry's leading theory for nearly a century because it seemed to explain things like metals and rust. When iron ore was heated in the presence of charcoal, phlogiston from the charcoal fused with the ore to form metallic iron. When the iron was exposed to air or water, the metal released its phlogiston as it rusted. Other metals went through the same process, forming the green verdigris of copper, for example. Ore plus phlogiston equals metal. Metal minus phlogiston equals rust, or what was then called a calx.
Only there was a problem. The calx was heavier than the metal, even though phlogiston had left the metal. It's lost something, and yet it was heavier.
The calx should weigh less than the original metal, but it doesn't. The calx is heavier than the metal.
Though many chemists were aware of this contradiction, they let it pass because phlogiston otherwise worked so well. But Lavoisier was really troubled by this because he was obsessed with the weights of his experimental ingredients.
Lavoisier was very careful to get very good instruments. He probably at one point had the largest and most complete private laboratory on Earth.
With my precision scales, imported from England at great expense, I measure the weight of each substance at the beginning and end of every chemical reaction.
Lavoisier was a master of this balance sheet kind of chemistry. Remember, he was a tax administrator by day. He knew a lot about accounting, and so this kind of ledger keeping was natural to him.
It is a fundamental truth of chemistry that the same amount of matter exists before and after each experiment. Nothing new is created, nothing lost. The whole art of performing chemical experiments rests on this principle.
Today we call this idea the conservation of matter.
When you carry out a chemical reaction, what comes out has to be exactly equal to what goes in.
The total weight must remain precisely the same. If not, there's an error somewhere.
He wasn't the first to assume conservation of matter, but Lavoisier applied this idea more rigorously than anyone had before. And it worked very effectively as a tool of discovery.
The power of Lavoisier's method would become clear in October 1772, when he set out to solve the riddle of why metals gain weight when they form calxes.
Common sense suggested that when things rust, they must lose weight. They fall apart, they become brittle and weak. Lavoisier was interested in actually measuring what happened.
He conducted his experiments in public, relying on a huge burning lens that focused the sun's rays to produce intense heat, while elegantly dressed bystanders watched in amazement. Lavoisier placed a calx of lead mixed with charcoal inside a glass vessel partially filled with water, then subjected it to the intense heat of the burning lens. The result was extraordinary.
As the calx changes back into the metal, it releases a large quantity of air. This air forms a volume 1,000 times greater than the calx it came from.
This startling finding suggested a radical idea. If air came out as the calx changed back into a metal, could it have gone in when the calx was formed? Could air be the reason calxes were heavier than expected? Lavoisier also found that when he burned elements like sulfur, they too gained weight.
There was then no doubt. I realized that the increase in weight occurs because a portion of the air is absorbed into the solid material.
He knew he was onto something very important. He knew that the element did not lose mass, it gained mass. It took up some part of the air.
I felt I must secure my right to this important discovery. So I deposited a note with le secrétaire de l'Académie to remain sealed until I was ready to make my experiments public.
He's discovered what seems to be evidence by weighing things that seem to flatly contradict what the phlogiston theory is predicting.
Despite what our senses tell us, both rusting and burning involve absorbing something from the air, just the opposite of what chemistry's reigning theory held.
It had been known for 100 years that metals gain weight when they become calxes, but no one had bothered to really investigate this anomaly. By focusing so intently on weight, Lavoisier had challenged the very foundation of chemistry, and he'd identified the source of that weight gain. Air was somehow involved.
But was it air itself or some part of the air? And if so, what part? The identity of the mystery gas eluded him for 2 years. He was still stumped in late 1774, but the answer would soon be delivered by Joseph Priestley. By this time, Priestley had begun to study something called the Red Calcs of Mercury. Mercury is a strange metal, one of just 2 elements that is liquid at room temperature. But like other metals, it forms a calx, a red solid that pharmacists of the 1700s used to treat venereal disease. Chemists had noticed something unusual about this calx. They could convert it back into metallic mercury simply by heating it. No charcoal, no source of phlogiston was needed. This was theoretically impossible. How could it be? The ever-curious Priestley wanted to know. So in August 1774, he obtained a sample of mercury calx and used his own burning lens to heat it with sunlight.
That reddish substance in turn decomposes, giving back mercury, but also a gas.
Priestley collects this air because he likes to test these gases and to see what properties they have.
If it were his old friend fixed air, the candle would go out.
But what he found about this air was it had quite extraordinary properties.
What astounded me was that the candle burned in this air with remarkable vigor. The flame was bigger and brighter than in ordinary air.
Something in this air seems almost better than normal air, which is very puzzling.
I was utterly at a loss. How could I explain this?
Eh bien, chers amis, buvons à la santé d'Archimède.
Dr. Priestley, have you been to the continent before?
No. This is my first time.
2 months later, on a visit to Paris, Priestley was invited to dine with members of the Royal Academy of Sciences, including Antoine Lavoisier.
J'ai récemment réalisé.
Priestley tells Lavoisier in his very broken French about his new discovery.
Avec les résultats très intéressants. I described this experiment at the table of Monsieur Lavoisier. I never make the least secret of anything I do. Le même air de plum rouge.
Everything that he came up with, every new experiment that he did, even when he wasn't sure what the results meant,
Qu'est-ce que c'est ce plan rouge?
he was constantly sharing that information with as many people as possible.
Mais, à ma grande surprise, I also told them that it produced a kind of air in which a candle burned much better than in common air. Mieux que dans l'air commun. At this, the entire company, including Monsieur and Madame Lavoisier, expressed great surprise. I'm sure they cannot have forgotten these events.
Monsieur Priestley, êtes-vous bien sûr que ce n'était pas l'air fixe?
If you want, I can translate for you.
Ah, merci.
Are you sure that what you found was not fixed air?
Absolutely. But I'm not yet sure of what it was.
Lavoisier did not appreciate Priestley's style. He didn't think Priestley brought very much thought to his scientific foraging.
But Lavoisier was smart enough to recognize that Priestley was onto something and take that piece of information and go back to his lab to figure out exactly what Priestley had discovered.
Could this be the gas he was looking for? The one involved in rusting and burning? Lavoisier hurried to the local apothecary to buy his own sample of mercury calx.
Now, tricky part.
Back in England, Priestley dithered for months on other projects,
Look what you can do.
unaware he was in danger of being scooped. Finally, it occurred to him, if this gas he had discovered supports fire, might it also support breathing?
Here we have one of the great discoveries in the history of chemistry, and the scene is kind of amazing. You've got this man and a mouse.
I put a mouse into a glass vessel containing 2 ounces of the air from the heated calcs of mercury. If it were common air, a full-grown mouse would have survived in it perhaps a quarter of an hour.
15 minutes pass. 20 minutes pass.
In this air, my mouse remained perfectly at ease for a full half hour.
That's twice as long as any mouse has ever survived.
I began to suspect that the air into which I had put the mouse was better than common air.
He takes the same mouse, sticks it back under the glass, and sure enough, the mouse survives another 30 minutes in this strange new air. He realizes that something fundamentally different has happened. This air is some kind of super air.
I concluded that this air was between 5 and 6 times better, that is, more breathable than the best common air I'd ever tested.
He finally has kind of convinced himself this air must be safe to breathe if the mouse is doing so well. And so he gets up enough courage to actually try it himself.
It doesn't feel any different from common air when I breathe it in. But I feel peculiarly light and easy. In time, this pure air may be useful as a medicine or sold to the fashionable for recreation. Up to now, only 2 mice and I have had the privilege of breathing it.
As Priestley is conducting these experiments in England, across the channel, Lavoisier is basically going through the exact same experiments.
Lavoisier, realizing that this is essentially the key to the mystery, gets to work on it.
3. I found, much to my surprise, that this air had none of the properties of fixed air. A candle burned in it with a dazzling splendor, And charcoal, instead of just smoldering, threw sparks in every direction.
Lavoisier announced his findings with great fanfare at the 1775 Easter meeting of the Academy of Sciences.
All this evidence convinced me that this air is more breathable, more combustible, and more pure than even the common air in which we live.
And he gives it the name oxygen.
In announcing his findings, Lavoisier made no mention of Priestley's revelation over dinner 6 months earlier.
Now, Priestley is not a shrinking violet here. He hears about this and he objects.
He should have acknowledged that my account over dinner led him to try the experiment. One should not put one's scythe into another man's harvest.
I admit I was not the first to do these experiments. That claim goes to Mr. Priestley. But from the results, we have drawn diametrically opposite conclusions. I may be criticized for having borrowed from the work of this celebrated philosopher, but I trust that the originality of my conclusions will not be challenged.
Lavoisier was right. While it was Priestley who made the discovery, it was Lavoisier who grasped the implications of this new gas.
Trois.
Lavoisier was the only one who understood what was going on. Perhaps he didn't understand perfectly, but the moment that new element, which we call oxygen, was there, he picks it up and he runs with it.
Over the next 15 years, Lavoisier would show that air is not a simple substance, as the ancients believed, but a mixture of two newly discovered gases. That water, too, was a product of two gases, and that fire is not an element, but a process of combining with oxygen. Even the solid substances the ancients had lumped under the heading earth were now seen in a new way.
Metals like iron and tin and lead had been known for centuries. But in the era of phlogiston, they were thought to be compounds because they had phlogiston in them. Lavoisier had turned this picture upside down. He showed that by stripping away the oxygen from the ore, you got down to the simpler metal within. The metal, not the ore, was the element.
So all four of the ancient elements, air, water, earth, and fire, had been abolished, thanks to the discovery of oxygen.
Once you accept the existence of oxygen, the main difficulties of chemistry appear to evaporate. Well, if all of chemistry can be explained without phlogiston, in all likelihood, it doesn't exist.
For years, many chemists, including Joseph Priestley, refused to abandon the old theory. What finally won the day was the textbook Lavoisier wrote in 1789 to spread his new chemical theory. As it was adopted around the world, phlogiston quietly passed into history.
So the old chemical system has been essentially destroyed.
Though Lavoisier is often given most of the credit, it was really both these men, working in their very different ways, who brought about this chemical revolution.
They kind of needed each other in a way. For science to work, you need both kinds of scientists, right? You need the scientists who are great systematizers, and then you need the mavericks and the tinkerers who are going to open up new doors for discovery.
One of the doors Priestley and Lavoisier opened was a fresh way to tackle that old question, what is the world made of? It was clear now that rocks of every conceivable variety might harbor undiscovered elements chemically fused with oxygen.
People realized that if they could release oxygen from other substances, what was left behind might be some of these missing elements that everybody knew must be out there.
How many more elements might you find by stripping away the oxygen that like to bind to so many things?
Lavoisier's textbook included the first modern list of elements, 33 simple substances. Some, including light and heat, were later found not to be elements. But it was a start, and it served as a challenge to other chemists.
Now that they knew how to look for them, chemists began to ask, what are the elements? The question had never been asked before in exactly that way. And so the discovery of oxygen really served as a starting gun for a worldwide race for new elements.
All over the world, chemists and amateur collectors responded to Lavoisier's challenge, rapidly identifying 15 new elements. From Sweden to Mexico, Connecticut to Siberia, the discoveries kept coming, sometimes as many as 4 in a single year. And few things could bring a chemist more glory than identifying a new element.
Well, certainly, Lavoisier was one of the great masters of all time. In fact, his greatest.
One of those who would soon be caught up in the hunt was a precocious chemist from the farthest reaches of England.
Pathetic ideas of phlogiston. Huh?
I've just met a remarkable young man whose talents I can only marvel at. He's not even 21 and has been studying chemistry for no more than 18 months, but he's advanced with such strides as to overtake everybody. His name is Davy, the young chemist, the young everything.
Humphrey Davy was the son of a simple woodcarver from the remote seaside village of Penzance, about a week from London by stagecoach.
Penzance is right down in the far southwest corner of England. And in some sense, it was the Wild West, right out beyond the influence of London and its institutions.
When his father died young, Humphrey left school at 16 and took a job as an apothecary's apprentice to support the family. But he never lost his love of learning. He simply resolved to teach himself.
The same year that Davy's father dies, Lavoisier publishes his elementary treatise on chemistry. And young Davy reads this in the original French. He starts keeping notebooks from this very date, and there's a kind of intellectual explosion.
Chemistry arose from the delusions of alchemy only to be bound by the chains of phlogiston. But through the discoveries of Black, Priestley, and Lavoisier, it has now been liberated.
Davy started doing experiments right away. One of the things he did was to attack Lavoisier's theory of heat.
Lavoisier said it was a material substance called calorique. And Davy didn't believe this.
Davy thought that he could take on the great man. He thought heat was motion of particles, and he thought he could prove this if he could rub 2 pieces of ice together. So no heat would be coming in from outside, and the sheer friction would melt the blocks of ice. And that's what happened. To him and his contemporaries, the experiment was a convincing one.
Davy's findings, written up in his first published work, showed enough promise to land him a post closer to Britain's center of action, in Bristol, at the Pneumatic Institution.
So he leaves remote Penzance to become the assistant and then the director of this new institute. He's only 19, for heaven's sake.
The institution had been founded in the hope that some of the gases discovered by Priestley and others would prove useful in treating diseases. Davy's job was to make the gases and then test them.
I took just 3 breaths of the gas. The first produced a feeling of numbness.
One of the gases he tested was mostly carbon monoxide, the poisonous gas now found in auto exhaust.
He doesn't know exactly what it is, but he makes it and he tests everything on himself. It's amazingly reckless, but it's also very brave.
He acted as if in sacrificing one life, he had 2 or 3 others in reserve. Some days I half despaired of seeing him alive the next morning.
And then he takes his pulse and he says, "I do not think I shall die." And he's ill for 48 hours, but he survives. On a number of occasions, he does nearly kill himself.
When you've got a career to make, and you're coming from a low point down the social scale, you've got a long way to go, why not take a few risks? Get your way up to the top quicker.
The top Davy had in mind was the very pinnacle of science. On one page of his Bristol notebooks, he wrote his own name next to that of the most famous British scientist of all time.
Newton and Davy.
So he has this sense that he and Newton can go at science together. It's not arrogance exactly, it's this tremendous drive, and he passionately believes that he will be a sort of Newton in chemistry.
I don't hesitate at all. The great master made a few mistakes.
All his life, that drive is there. Newton and Davy.
In Bristol, Davy sought out a group of literary men whose work would define the Romantic Age, including publisher Joseph Cottle and poets Robert Southey and Samuel Taylor Coleridge.
The assumption that heat is a simple substance. Is that what he called caloric? Precisely.
In looking at that group in Bristol, one of the things I think is wonderful, there was no gap between the writers and the poets and the scientists.
We can discover that the ice melts by friction alone.
Now, Davy, could not the melting have been caused by the temperature of the room?
That's a very good question indeed, one to which I have a ready answer. The air.
Every evening they're going out, they're writing letters to each other, going on walks together, and they're young men with a future. There's an extraordinary group.
In Davy, these romantic poets found a kindred spirit.
When we remove the ice from the point of friction, it refreezes.
A scientist who shared their sense of wonder at nature and yearned to reveal her mysterious ways.
Heat must, in fact, be the motion of particles.
There's an energy, an elasticity in his mind that allows him to seize on and analyze all subjects. Living thoughts spring up like turf under his feet.
Early in his research, Davy produced a gas one medical authority had warned was the cause of terrible diseases. He tried it anyway.
This evening I breathed nitrous oxide and experienced a thrilling all over me, more pleasurable than anything I have ever experienced. The objects around me became dazzling and my hearing more acute. Sometimes I responded by stamping my feet. Other times by dancing around the room and laughing uncontrollably.
As word of his discovery spread, many others, from steam engine pioneer James Watt to the king's own doctor, clamored to try Davy's laughing gas.
Coleridge and Southey both took doses of the gas. It was very much in keeping with this romantic time period.
He's invented a whole new pleasure. It makes you laugh and tingle in every toe and fingertip.
There was a certain amount of recklessness experimenting with drugs. Why not expand your consciousness?
It makes you strong and happy, so gloriously happy. Oh, excellent airbag. I'm going for more this evening.
Davy asked each of his subjects to record their impressions.
The first time I tried nitrous oxide, I felt a highly pleasurable sensation of warmth over my whole body. It was like the feeling I once experienced entering a warm room after returning from a walk in the snow. I felt no desire to move, only to laugh at those who were looking at me.
Davy wrote up their accounts in his first true scientific book. But just as he was finishing the book, Davy's attention was diverted by a discovery that would shake the very foundations of science. In 1800, an Italian named Alessandro Volta announced that he had created a new source of electricity. Up to then, the only sources of electricity had been lightning, which was very difficult to tap, and electrostatic devices, like the ones Priestley had used.
You could get quite spectacular effects in the way of flashes and bangs.
How are you doing that?
But you couldn't get sustained power. What Volta did was to establish that electricity was something that you could make a steady supply of, what we call an electric current.
Volta's device was incredibly simple. A sandwich of alternating copper and zinc discs separated by pieces of cardboard that had been soaked in salt water. But this voltaic pile, the first battery, electrified the world of science.
With the battery, you could now perform a variety of experiments that had never been possible before. And these experiments were done immediately.
Just weeks after learning of Volta's discovery, 2 British scientists used a crude battery like this one to split water into its 2 elements, hydrogen and oxygen.
The electric current was somehow breaking up the water into its components.
Even more surprising, the hydrogen collected at the negative electrode over here, and the oxygen collected at the positive electrode over here. Why would these 2 elements show a preference for opposite electrical charges? Intrigued, Davy set aside his research on gases, built a voltaic pile, and began doing his own experiments on electricity.
And it became Davy's big pursuit in life. What could this electric current do?
Volta has given us a key to some of the most mysterious recesses of nature. Till this discovery, our tools were limited. Now, the possibilities for chemistry seem boundless. It's like an undiscovered country, a land of promise.
Davy had just begun to explore that land when opportunity knocked. His book on nitrous oxide had caught the attention of the founders of the new Royal Institution in London, who were looking for a director for their chemistry laboratory.
And that book had such impact that it was read in London, here at the Royal Institution. It's very, very precise. It's measured, it's quantitative science, and they thought, this is the man we must get.
Still only 22, Davy set out on his next great adventure, leaving Bristol in 1801 for the city he called the great hotbed of human power.
When Davy arrived, his patrons seemed to be a bit taken aback to find this still rather raw country youth. But his natural eloquence must have come through and eventually charmed them.
One of the missions of the institution was to offer public lectures meant to stimulate an interest in science among the London elite. For this purpose, a theater had been installed in the institution's building on Albemarle Street. Davy started out as assistant lecturer, seen here helping his boss give a dose of laughing gas to one of the patrons. But with audiences shrinking and the institution's fortunes flagging, Davy was quickly promoted to the top job.
Nothing is so fatal to the progress of the human mind.
Determined to make the most of this opportunity, he set out to make each lecture seem spontaneous.
But to do spontaneous, what he did was prepare.
As to suppose that there are no new mysteries left in nature.
And he would read through, in front of his assistants, drafts of the lecture to see if it worked.
Who would not want to learn the most profound secrets of nature, to ascertain her hidden operations?
The moment Davy began to lecture, the audience is packed in.
Conquer. Science has done much for man, but it is capable of doing still more.
He had people absolutely lapping up what he was pouring out.
There were other chemists giving public talks elsewhere in London, but none held a candle to Davy.
He must have directed his bright eyes around his audience so that they felt really drawn in and mesmerized. And he would do dazzling experiments that he carefully rehearsed with his assistants the night before, so they always worked.
And people gasp, and they cheer, and they clap at the end of a demonstration. It's so brilliantly done. And these lectures became hugely popular. There were the most terrible traffic jams outside the Royal Institution. Albemarle Street became the first one-way street in London because there were so many carriages bringing people to listen to his lectures.
He was young, he was handsome, he was eloquent, and there were a number of young ladies in the audience.
And they're all in the front rows making notes, but hanging on Davy's every word. Among the lecture notes in the Royal Institution archive are these little billets doux, little love letters, often signed with a pseudonym, and poems to him.
One of his female admirers invited him to dinner, noting, Those eyes are too fine to be forever gazing over crucibles.
I have audiences of 400 or 500 people, many of high rank, and I suspect that some of them may become permanently interested in chemistry. This science is becoming the fashion of the day.
Davy's success as a lecturer and entertainer brought him wealth, prizes, and acclaim. But he was growing impatient. Giving popular lectures was no way to become the Newton of chemistry.
By 1806, he'd established enough of a reputation, and he knew that his work was supporting the Royal Institution. He could say, right, I've known your work for the last 5 or 6 years. Now I'm going to do my own work.
An invitation from an organization once headed by Newton himself gave Davy the perfect chance to show what he could do.
He was asked to lecture not to the Royal Institution, but to the Royal Societies, the top scientific group in the world. He needed to produce some dramatically original science.
With this goal in mind, Davy dived into the subject he'd been itching to return to ever since Bristol: electricity.
Up to now, we have studied electricity only in its most powerful form, lightning. But its slow and silent operations on the Earth's surface may prove more important.
From his early experiments, Davy had learned that an electric current could pry apart the hydrogen and oxygen atoms that made up water.
You can use a battery to unbond things and find out what the different elements are.
That gave Davy an idea. Could he use a bigger battery to tackle substances that were harder to break down?
This is something you can do with this new source of electricity. If a small battery gives you a small effect, build a larger one and you get a larger effect.
As the target for his experiment, Davy chose caustic potash, a substance derived from wood ashes collected in a pot. Chemists had long suspected it contained an undiscovered element, but no one had been able to break it down into simpler stuff.
He believed that if you could apply a charge to it in some way, you would discover something about its inner nature.
So Davy constructed a really big battery because he wanted to see whether potash could be decomposed into its elements.
Davy was thus able to use the resources of the Royal Institution to undertake scientific research, which had never been the intention of the founders of the RI.
But by the time he began the work, his Royal Society lecture was only a month away.
Shall we? He committed himself rather recklessly because he didn't really have much time.
Would this new battery be strong enough to reveal what potash was made of?
Working at top speed, he tries various ways of applying the charge.
Davy first tried putting a current through a mixture of potash and water. All that did was split the water into hydrogen and oxygen.
Do you see anything?
Leaving the potash unaffected.
And then he tried with dried potash. And again, nothing happened.
Finally, he moistened the dry potash just a bit before applying the electricity.
Dry potash won't conduct electricity, but when I added a little water and applied a strong electrical current, I soon observed a vivid action. There was a violent effervescence and small globules.
It sweats forth these glowing, shining globules.
They have a metallic luster, very much like mercury, and some of them exploded and burnt with a bright flame. I realized these globules were the substance I had been searching for.
And this is a new element, in fact. It's potassium, one of the crucial elements for life, and he's discovered it. There's a wonderful description made by his assistant, who was actually Edmund Davy, a young cousin. He said, the professor became a boy again.
When he saw those globules of potassium burst through the crust of potash and catch fire, he couldn't contain his joy. It was some time before he could compose himself and continue with the experiment.
And you get the sense of this huge excitement, doing things under pressure, not quite knowing what will happen, whether the damn thing will explode. And then suddenly the unknown reveals itself.
The atoms of potassium and oxygen, so firmly glued together, could be separated by an electric current in the same way as those oxygen-hydrogen atoms in water.
The very next day, Davy used the same method to pull apart caustic soda, or lye, to reveal another new element, sodium. These two new metals were so soft they could be cut with a knife, and so eager to recombine with oxygen that they gave Davy the perfect demonstration for his next lecture.
Are we ready for anything? All right.
Davy had turned electricity into a powerful tool in the search for new elements. The year after discovering potassium and sodium, he used his battery to isolate 4 more elements, and chemists all over Europe seized on his technique, sending the number of elements even higher.
Sometimes the progress of science is due less to our intellectual powers than to the tools at our disposal. Nothing promotes the advancement of knowledge so much as a new instrument.
Exciting as these discoveries were, in time it would become clear that Davy's greatest contribution was his insight into one of the biggest questions in chemistry.
Somehow, the particles of matter have to be glued together to form molecules, and it was a complete mystery as to what this glue might be. What Davy has had, in effect, is a big idea.
If electricity could pry apart the atoms in water, potash, and soda, might electricity be the force that stuck those atoms together in the first place?
Is electricity an essential property of matter?
Perhaps electricity, with its plus and minus aspects, could be this kind of glue.
In every case that we know of, substances that combine with each other have opposite electrical states. And perhaps this is the reason they're attracted to each other, because opposites attract.
It looked as if electricity might play in chemistry the sort of role that gravity played in Newtonian physics.
Remember, he thinks of himself as on a par in some way with Newton. He's going to be the Newton among chemists. And in a sense, he does eventually achieve that.
In the 18th century, electricity was mostly parlor tricks, like making somebody's hair stand on end and attracting little bits of paper and so on. Davy showed that electricity is a fundamental aspect of matter. Electricity is what holds us together. It is the glue that links the particles of matter. And therefore, instead of being rather a side thing, electricity is going to be one of the really central features of science.
It would take more than a century for other scientists to figure out electricity's role. But after Davy, there was no doubt it would be one of the keys to solving the mystery of matter. One of the oldest tricks in the chemist's toolbox is called the flame test. More than 1,000 years ago, Arab alchemists discovered that every substance gave off a telltale color as it burned. But as the number of elements grew, this test became less and less useful, because some elements gave off such similar colors it was hard to tell them apart. One day, in 1859, a German chemist named Robert Bunsen described this problem to his good friend, physicist Gustav Kirchhoff. A few days later, Kirchhoff came to Bunsen's laboratory with an instrument made from 2 telescopes, a wooden box, and a prism. They used Bunsen's latest invention, the Bunsen burner, to heat their samples. Light from the burning element passed down the barrel of this telescope to the prism, which split the light into a spectrum of colors. What they saw when they looked into the eyepiece was a revelation.
you see a whole collection of sharp, bright lines at very particular wavelengths. And that map of lines is distinctive for every element.
It's almost like each element has its own barcode. It's a unique way of saying this is that element, not some other.
Like Humphrey Davy's battery, the spectroscope kicked off a whole new round in the discovery of elements. Starting with cesium and rubidium, discovered by Bunsen and Kirchhoff themselves, quickly followed by thallium and indium, discovered by other chemists who seized on their new tool. Astronomers, too, embraced the new technology, turning the spectroscope to the heavens.
In fact, there's one element that we found by first looking at the sun. We didn't even know it was here on Earth. It was helium.
By the middle of the 19th century, there had been an explosion in the numbers of new elements that had been found. And this was exciting, but it also led to a kind of muddle. It seemed to have no order, no reason behind it.
Chemistry looked like an unruly garden, a jungle of bewildering details.
Human beings like to make things simple, and part of the whole scientific enterprise is to bring order out of what appears to be chaos, to bring simplicity out of complexity.
But the ever-rising number of elements, now up to 63, promised chemists just the opposite of simplicity, more and more variety, with no end in sight.
How many elements were there? Was this going to continue forever?
The man who would finally bring order to the elements was a young Russian chemistry professor named Dmitry Mendeleev. He didn't set out to be a savior. He was simply trying to organize the textbook he was writing. But as he grappled with this challenge over one weekend in 1869, Mendeleev would make a discovery for the ages: the periodic table of the elements. Today, it hangs in every chemistry classroom in the world, one of the most familiar images in all of science. But behind the table is a fascinating, untold story. Who was this man, and how did he do it? Mendeleev had recently been named a professor at the University of St. Petersburg, the leading institution in Russia's capital. But getting there had been a long, improbable journey from humble beginnings.
Mendeleev was born in Tobolsk, Siberia, which is basically smack in the middle of Russia if you look at it on a map. It's very much the boonies of Imperial Russia.
His father, the headmaster of the local high school, went blind during the year of Dmitry's birth, leaving Mendeleev's mother to support and raise about a dozen children. Maria Mendeleeva sensed something special in her youngest child. So in 1849, she set out with her 15-year-old son on a 1,500-mile trip by horse-drawn sleigh in search of a school that would accept him. Like most students from the provinces, Dmitry was turned away in Moscow. But in St. Petersburg, he landed a spot in the teacher training school his father had attended. Exhausted by the journey, Maria died a few months later.
She took me out of Siberia and sacrificed what remained of her money, her life, so that I could get an education. From her, I learned that it is through work, not words, that we must seek divine and scientific truth.
Scientific truth was elusive for any young chemistry student in the mid-1800s. There were deep divisions in the field over even the most basic concepts, particularly the atomic weights of the elements. Most chemists believed each element had its own unique kind of atom, and ever since the early 1800s, they'd been working to determine how much an atom of each element weighed.
That's how one distinguished one element from another. So it was crucial to understand what were the correct atomic weights for each of the elements.
Everyone agreed that hydrogen, the lightest element, should be assigned a weight of 1, and that heavier elements should have proportionally higher weights. But that's where the agreement ended.
Did carbon weigh 6 or did it weigh 12? Did it weigh 4? That depended on who you talked to and when you talked to them. By the late 1850s, people were incredibly confused.
This was an unsupportable situation. Something had to be done.
Hoping to sort out the mess, chemists organized their first ever international meeting, held in Karlsruhe, Germany in 1860.
Mendeleev, being a young enterprising student, goes to this meeting and he hears a very important speech by an Italian chemist, Stanislao Cannizzaro.
Cannizzaro laid out a persuasive case for a new uniform system of atomic weights.
I still remember the powerful impression Cannizzaro made. He seemed to advocate truth itself.
After Karlsruhe, something astonishing starts to happen. Within a few years of the Congress, you start seeing lots of different attempts to organize the elements that are all based on these new post-Karlsruhe weights.
A French geologist arranged the known elements in a spiral along the outside of a cylinder, like the stripes on a barber pole, and found that elements with similar properties tended to fall into columns. An English chemist arranged the elements by atomic weight in rows of 7, and found that their properties repeated like musical notes 1 octave apart. By the end of the 1860s, 5 different European scientists had detected glimmers of a hidden order among the elements, but no one could quite put the puzzle together. That's where things stood when Mendeleev finally landed a professorship at the University of St. Petersburg. One of the duties of his new post was to teach introductory chemistry.
He has to teach this class, hundreds of students, and he has to give them a textbook. There are no up-to-date Russian language college-level textbooks available.
So Mendeleev set out to write his own, Principles of Chemistry, in 2 volumes. He completed the first volume in 1868, and on Friday, February 14, 1869, he sent the first 2 chapters of Volume 2 off to his publisher.
Marina.
He was in a hurry to finish it because he was struggling to make ends meet.
He hasn't yet gotten any royalties from the textbook because it hasn't been written yet. He's got to keep his family fed and clothed. He has, at this point, 2 children and a wife, so he was always looking for more funds.
To make a little extra money, Mendeleev planned to take a short break on Monday to do some consulting for a cheesemakers cooperative. But he had something on his mind. His publisher was expecting the next chapter of his textbook in 2 weeks, and he still hadn't settled on a way to organize the rest of his book. Mendeleev had spent most of the first volume covering a few common elements like hydrogen and oxygen in great detail.
You learn a huge amount of chemistry, but it's slow. Volume 1 contains just 8 elements out of the 63 that were then known.
When it came to writing the second volume of his textbook, Mendeleev realized that he had better find an organizing principle fairly quickly because he had to cover the remaining 55 elements.
Since I'd set out to write a book called Principles of Chemistry, I felt I had to establish a system for classifying the elements. A system based not on chance or guesswork, but on some sort of principle.
The problem gnawed at him all weekend.
He's trying to come up with a way of packing more elements in the same amount of space. He couldn't ramble the way he did in Volume 1, however useful that was.
Mendeleev had already hit on the idea of focusing on whole families of elements rather than treating one at a time. Chemists had long known that certain elements resemble each other in much the way family members do.
You can often tell people are related because they have the same sort of face.
They have the same nose, they have the same color eyes. There's something in common, and that's something very similar in these chemical families. They tend to react similarly to the same kinds of substances.
Mendeleev had ended Volume 1 with 2 chapters on a well-known family, the halogens: chlorine, fluorine, bromine, and iodine. He began Volume 2 in the same way, with chapters on sodium, potassium, and lithium, a family called the alkali metals.
He realized that a family of elements is a good way of organizing so you can do more with less space.
The problem was there was no obvious family to turn to next. For insight into what other elements might be grouped together, Mendeleev looked more closely at the 2 families he already had.
And in that process, he figures out something rather extraordinary about the elements. He looks at the atomic weights of sodium and lithium and looks at the difference between them. And then he does the same thing for fluorine to chlorine and notices that those two differences are very close to each other.
Was this just a coincidence or a clue? Excited, Mendeleev wrote down the lightest elements and their atomic weights. After 7 elements, he broke off and started a new row, keeping elements with similar chemical properties in the same column. The numerical pattern continued to hold.
The eye is immediately struck by a pattern, a regular change in the atomic weights of the elements within the horizontal rows and the vertical columns.
He notices that there's a regularity in the differences. That is, the changes that happen within a family happen regularly across families. And that's the fundamental insight that gets him thinking about how to organize all the other elements.
Mendeleev had begun the weekend trying to solve the problem of what to do next in his textbook. But having reached this aha moment, he dropped everything else and he poured all his energy into revealing an absolutely fundamental principle of nature.
When he was taken by an idea, he was really taken by it. He starts putting together this system, and he's trying to figure out the hard spots, the things that don't quite make sense. Maybe I can scratch out this element here and put this element in its place. Should I change the atomic weights? Do I have to rethink their properties? And the problems of it, the intellectual puzzle, just grabs him.
The challenge Mendeleev faced was similar to one of his favorite diversions, the card game called Patience, in which the object is to arrange playing cards by both suit and number.
That process of keeping several different variables in mind is kind of analogous to how Mendeleev was thinking. He started using both the regular increasing order of atomic weights and the relationships of chemical properties with each other to build 2 dimensions.
Mendeleev didn't just lay out the known elements in order of rising atomic weight.
When it looks like the next element doesn't have the properties it's supposed to have, he scooches it over and leaves a blank spot.
And has the audacity, has the daring to suggest that there might one day exist an element that would fill that space.
The few scraps of paper left from Mendeleev's struggle that weekend reveal that he sometimes arranged the chemical families in rows instead of columns. Unhappy with this early attempt at a table, he moved the alkali metals to a new position in the next draft below, but kept them together.
Mendeleev is not moving elements individually, but he's moving them as a block. It's as if it's a composite piece of a jigsaw puzzle that he's moving all together.
On Monday morning, a driver arrived to take Mendeleev to the train station for his trip to the cheese cooperative. He was well into his task, but still struggling to make all the pieces fit. We know this because one of the surviving fragments is a letter delivered that morning concerning arrangements for his trip to the cheese cooperative.
And on the back of the letter, which still bears the stain of a cup, Mendeleev has sketched a few symbols and has carried out some very simple calculations. He's looking at differences in atomic weights.
So he was still working on the problem, even after wrestling with it all weekend.
Карета ждет вас внизу.
The drafts of Mendeleev's table show plainly the struggle he went through.
At the bottom of the page, he lists the elements to be classified. As he fits them into the table on that page, he crosses out the elements. It's just what you and I would do. We can see the effort in that page. He's making mistakes, he's correcting them. It's full of crossings out. There are things that don't quite fit. This is a human being trying to understand this world.
Hour after hour, Mendeleev worked on the table, missing one train after another. Finally, he dismissed the coachman. The cheesemakers would have to wait.
Кто там? Александр Алексеев приехал.
Дмитрий Иванович, здравствуйте.
That afternoon, a visitor found him distraught. unable to capture the order he knew was there, just out of reach.
Не могу найти.
Later that day, Mendeleev came to a choice that would crystallize his thinking. The elements involved were iodine and tellurium.
Iodine's a little lighter than tellurium, so it should come first. But Mendeleev looks at that and says, well, if I put iodine first, it's in the wrong family. It's actually a halogen, which is the next row down.
If he stuck to that weight rule, it would put an element outside of the family it obviously belonged in.
So he decides tellurium, the heavier element, should go first. It always bothered him that iodine was lighter than tellurium but came after. That breaks the order of atomic weights, but it preserves the family resemblances, which are more important than just the increase of atomic weights.
With that principle established, Mendeleev hurried toward the end.
And the more he worked on it, the better it looked.
Finally, that evening, Mendeleev completed his table. Before leaving the next day, he ordered 200 copies printed and sent to leading European chemists.
By the time he left for the cheese factory, Mendeleev knew that he was onto something extremely important. I think he realized that day that he had cracked it.
With a few modifications, soon made by Mendeleev himself, his 1869 draft is easily recognized as the periodic table of the elements, incomplete but unmistakable. In his published table, Mendeleev left blanks for some of the elements he thought were missing.
Not only did he leave a blank space, but he suggested an approximate atomic weight for that future element.
And the fact that Mendeleev on that first weekend is already thinking this way, that's a sign that he believed that there's something deeper going on here.
Mendeleev believed his table was more than a convenient way to arrange the elements. He was convinced he had discovered a law of nature, that the properties of the elements are determined by their atomic weights and vary in a regular, periodic way across the table.
It's periodic because the properties of the elements repeat in a regular fashion. When you wrap around from one row to the next and come back to where you were, the elements that are in the same column have similar properties.
He had an almost mystical feeling that this was there in nature and not so much a human invention as a discovery.
Given the remarkable regularity of his table, Mendeleev couldn't believe nature would have just left some spaces empty.
Laws of nature do not permit exceptions.
There must be an element which we have not yet discovered. Go look for that element.
And he was bold enough to not only to say an element is missing, but to predict.
The periodic law allows us not only to predict what new element will be found, but also to determine in advance their chemical and physical properties.
In 1871, Mendeleev published an article making predictions about 3 of the missing elements based on the properties of their neighbors in the table.
Chemists really weren't used to making predictions of any kind, let alone ones to this degree of specificity. They are remarkably precise and quite daring for Mendeleev to print them.
4 years later, a French chemist found a new metal so soft it melted in his hand. He called it gallium. It seemed to be a good fit for the empty spot below aluminum, but the density didn't match Mendeleev's prediction. He wrote the Frenchman suggesting that he check his data.
So you can just imagine this Frenchman who actually has the element in his hands, hearing from this Siberian who has never seen the element, and daring to say to him that he's made a mistake.
But sure enough, when the French scientist rechecked his measurements, Mendeleev was correct.
So not only had Mendeleev predicted the element, but he knew the properties of the element better than the discoverer of the element knew them.
Within 15 years, all 3 of the detailed predictions are discovered, and that catapults Mendeleev to chemical superstardom.
I never thought I would live to see my ideas verified. I was wrong.
But in 1894, two British scientists made a discovery that threatened to bring Mendeleev's carefully crafted edifice crashing down. They found a new gas they called argon that didn't seem to fit into the table.
When Lord Rayleigh and William Ramsay discovered argon, it looked like a problem, a very serious challenge to the periodic table itself.
Mendeleev's first reaction to almost anything that was contradictory to the system was to be hostile to it and suspicious. And Mendeleev therefore decides it's not an element. There are lots of reasons to think that. First, it doesn't react with anything.
Chemists couldn't get it to do anything. It was inert. It behaved like no other gas that anybody had ever encountered.
And secondly, it has no place on the table, so how can it exist?
Matters got worse when Ramsay announced he'd also isolated helium, 30 years after it was first detected in the sun. It was definitely an element, and it too had no place in the table.
And then just 3 years after that, William Ramsay's research group discovered 3 new rare gases, krypton, xenon, and neon.
They display the same kind of properties, they're all inert gases, and they display the same increase of atomic weights as the other natural families do.
And that changed the situation dramatically. What began as a single anomaly, a single puzzle, now looked like a group of elements.
Now we can see that helium, neon, argon, krypton, and xenon are as closely united as any other group.
And so Mendeleev makes the single biggest revision to the system he ever did. He puts in a new column, and that is the family of noble gases.
My periodic system is in no way injured by these discoveries. In fact, they confirm and strengthen it.
It turned out to be a vindication of the periodic system, and if anything, made it even more profound, the discovery.
Mendeleev's table had finally brought order to chemistry's unruly garden.
After Mendeleev, one could see that each element had a place. It was a grand design that worked.
Chemistry wasn't just one thing after another, random substances we've dug up from the earth. They are interlinked in a complicated and rich way.
We are at the dawn of a new era in chemical science, approaching a new understanding of the still mysterious nature of the elements.
As the 19th century drew to a close, the periodic table's ability to corral the elements contributed to a growing sense that the work of science was just about complete. Most of nature's building blocks had been found, measured, and cataloged. Chemists agreed these elements had been and always would be the same, forever fixed, unchanging. All that remained was to fill in the few remaining blanks. Or so it seemed. In fact, this smug sense of satisfaction was about to be shattered by something and someone completely unexpected. She was the unlikeliest of revolutionaries. A graduate student, a woman from Poland, who had left her homeland to pursue her passion for science in Paris. Yet in 4 short years, her discoveries would transform our understanding of matter and make her one of the most famous women in the world.
She worked on something that was relatively obscure and turned it into a blockbuster. New elements, new properties, and a whole new way to look at the world.
The world would know her as Marie Curie, but she was born Maria Skłodowska into a family of Polish patriots at a time when Warsaw was under Russian rule. Poland had been literally wiped off the map, its residents forbidden to speak their own language or teach their own history. But Maria's family secretly defied the Tsar, speaking Polish at home and reciting patriotic poetry to preserve their Polish heritage.
She used to go by an obelisk erected in honor of the Russian people and spit on the obelisk on the way to school. So you can see Maria learned early to be a fighter and resistor.
The daughter of 2 teachers, Maria excelled in science and math. But in Russian-ruled Poland, women were not allowed to attend university, let alone become scientists.
Very, very few places in Europe or elsewhere had opportunities for young women to study science. So one of the few places that she could was, in fact, in Paris.
But because her family was too poor to send her, Maria would first have to work for 6 long years as a governess to support her older sister's studies. Only at age 24 did she finally get her chance.
She waited her turn and she didn't give up. And when the turn came, she took it.
I was lost in the great city. But the feeling of living there alone and taking care of myself without any help didn't depress me at all. I had been waiting for this opportunity for a long time.
Paris in the 1890s was like no other place on Earth, a living showcase for the wonders of science and technology. The city boasted such modern marvels as electric streetcars and telephone exchanges. At the laboratories of Louis Pasteur, scientists were conquering diseases that had plagued humanity for centuries. The Lumiere brothers were thrilling crowds with their new invention, pictures that actually moved. And rising above it all was the brand new Eiffel Tower, which would remain the world's tallest structure for nearly half a century.
Here was Paris, the kind of intellectual, artistic, technological capital of the universe. This is where the modern age was born.
She felt this precious sense of liberty. She could say whatever she wanted, go wherever she wanted. She took it all in and loved it.
Everything I saw and learned was a new delight to me. I had only one regret. The days were too short and went by too quickly.
Adopting the French form of her name, Marie, she enrolled at Paris's preeminent university, the Sorbonne, where she could study under the leading lights of French science. One of them was Gabriel Lippmann, a future Nobel Prize winner.
Another was Henri Poincaré, who was one of the leading mathematicians of the 19th century. One of her math instructors was a mountain climber, another was an aviator. These were exciting people, scientists who had exciting lives.
It was like a new world opened to me, the world of science, which I was at last permitted to know in all liberty.
Marie graduated first in her class in physics, and with Professor Lippmann's help, received a grant to do research on magnetism. A friend suggested she seek out a French physicist who had studied the subject and might have some lab space for her. The meeting would change her life.
Pierre Curie seemed to me very young, though he was 35 at the time.
I think it was pretty much electric from the beginning.
With all my heart, I thank you for your photograph. I showed it to my brother Jacques. Was I wrong? He finds you very fine, but he also said she has a very decisive look, maybe even stubborn.
Pierre Curie was a first-rate researcher, but he had never bothered to complete his dissertation and was content teaching at an industrial college.
He was diffident, modest, and shy. He was very much an outsider. He'd been homeschooled by his politically radical father, along with his brother Jacques.
In a family photograph, you see him with his brother. His head is resting on his hand. It's a pose of dreaming, as if he is looking at some inner vision.
Pierre was a man of ideas, not action. But he was galvanized by this young woman and pursued her as he had nothing else in his life.
It would be a beautiful thing if we could spend our lives near each other, true to our dreams, in science, where every discovery, no matter how small, lives on.
Pierre's proposal posed a dilemma for Marie. She had planned to get a first-rate scientific education in Paris and then return to her beloved Poland to teach and care for her aging father.
Her mother died of TB early on, and he was counting on Marie coming back.
Now this ardent young man was offering her an exciting life as a working scientist.
It was a decision that would mean abandoning my family and my country.
Marie had all those feelings of responsibility for her father, for her family, and then for Poland on top of that.
In the end, their mutual devotion to each other and to science overcame Marie's resistance.
She wrote one of her friends, "Fate has brought us together, and we simply can't bear to be apart."
The newlyweds left on a cycling honeymoon after a simple ceremony in 1895. By 1897, even with a toddler to care for, Marie had set her sights on getting what no other woman had ever received in France, a doctorate in physics. At the time, the world was abuzz with excitement over a new discovery: mysterious rays that had the power to see through solid objects.
You could, by this process, look at the bones inside of your living hand. It's as if you had a magical set of glasses that lets you see inside of living creatures, and that sparks the public imagination.
Doctors instantly recognized X-rays as an invaluable diagnostic tool.
There was a great rush of excitement from working scientists as well. In that first year, there were about 1,000 scientific articles published at a time when the entire physics community in the world was only about 1,000 members.
But with so many others doing research on X-rays, Marie felt it would be hard to make an original contribution.
And so she picked something that she could work on where there was less competition. In fact, no competition.
Just a year earlier, a French physicist named Henri Becquerel had discovered a different kind of ray given off by the element uranium. These uranic rays were powerful enough to penetrate thick black paper and create an image on a photographic plate. But the images were not nearly as striking as those created by X-rays, and they seemed to have no practical value. So after writing a few papers about this scientific curiosity, Becquerel dropped the subject, thinking it had been squeezed dry.
Marie just thought that this was a tremendous thing to work on, particularly as a graduate student.
This subject was attractive to me because it was entirely new. Little had been written about it.
There was another reason Becquerel's uranic rays appealed to Marie. She had spotted a clue that might reveal more about them. As you can see, air is normally a poor conductor of electricity. The current can't jump this gap, so the bulb doesn't light. But Becquerel had noticed his uranic rays had the mysterious power to charge the air around them, allowing electricity to leak across. The amount of electricity was incredibly small, about 1/trillionth the amount needed to light this little bulb. No meter of the day could measure it. But Marie had a secret weapon Becquerel didn't.
Right in Marie's own household was perhaps the world expert in how to measure tiny little electrical effects. The two of them, Pierre and Marie Curie, designed this really quite ingenious instrument to measure these very subtle electrical effects from her samples.
They placed a layer of uranium on a metal plate, then charged the plate with a battery. As expected, electricity leaked across the gap to the plate above. To measure this tiny current, the Curies would use this second device to create a matching amount of electricity. Inside was a special crystal that could generate its own tiny charge thanks to a phenomenon called piezoelectricity. More than 20 years earlier, Pierre and his brother Jacques had discovered that certain crystals give out electricity in response to pressure.
The amount of electricity generated when you squeeze or stretch that crystal depends precisely on how hard you press on that crystal. And that means you have a way to make a very, very sensitive measurement of minute little electrical currents.
By placing a weight on the pan below, Marie stretched the piezoelectric crystal inside the device. Then, by slowly relieving the tension, unstretching the crystal, she could generate a charge exactly offsetting the one coming from her uranium sample. She could tell the two charges were equal when the spot of light from this third instrument was at 0 on the scale.
Though it didn't look very pretty, this sort of pulled together little contraption was exquisitely accurate and could allow them to make measurements like no one else in the world.
But using these instruments required extraordinary concentration and dexterity. Ever so gradually, Marie relieved the tension on the crystal, while carefully watching the spot of light to keep the two charges in balance. and timing how long it took to lift the weight entirely off the pan. The faster she had to remove the weight, the stronger the activity of her test sample.
And that's why when you see pictures of Marie Curie in this experiment, she's sitting there with a stopwatch.
C'est bien.
Oh, la petite étudiante. C'est très bien. C'est encore.
I never dreamt that I was about to embark on a new science that Pierre and I would follow for the rest of our days.
Day after day, working in a cramped, unheated storeroom, Marie painstakingly carried out her measurements. She compiled data on uranium, then went on to test the other known elements to see if any of them could also electrify the air.
She was not expecting to make any sort of earth-shattering discoveries.
She thought she would do some sort of diligent work on a whole lot of elements, and she would measure their power.
Exactly what you'd expect for a perfectly legitimate PhD dissertation.
And for a while, the results were predictably dull. No other elements showed this strange property.
Things were going along pretty routinely until one day in February of 1898, and that was the day that everything changed.
Pierre, viens voir.
In the course of a single week, Marie made two startling discoveries. She found that the element thorium could also make air a better conductor.
That was the first real solid indication that this was not unique to uranium. This might be a property of matter, not a curiosity of one particular element.
It was necessary to find a new term to define this new property of matter. I propose the word radioactivity.
The next surprise came when Marie tested pitchblende, the raw ore from which uranium is taken. Something was very wrong.
Comme ça, t'es sûr des résultats?
Je ne suis pas sûre.
Pitchblende seemed to be 4 times as radioactive as uranium itself.
When I find a result like that, as a scientist, my first reaction is, I made a mistake, or the machine isn't working.
She did what every good scientist should do, which was doubt it, be extremely skeptical, and check every last step of that chain.
So my mother made her measurements over again, 10 times, 20 times, until she was forced to accept the results.
In time, the Curies realized this was no mistake. The readings from pitchblende were real.
A light bulb went off and they said, well, maybe there's something else in there.
Very soon, they began to suspect that there was another element in pitchblende, which was producing this enormous radioactivity.
There must be some new thing under the sun, some new element that had never been seen before.
And it must be intensely radioactive, since it was present in amounts so small that no one had ever detected it.
Since neither Marie nor Pierre was a member of the Academy of Sciences, they asked Marie's mentor, Gabriel Lippmann, to deliver the paper announcing this discovery.
This was one of the most important papers in the history of chemistry, and yet it was almost universally ignored.
Who was this Marie Curie? She was a graduate student. She spoke French with a Polish accent. She was married to a teacher in an industrial school, and she was a woman.
These are strikes that are definitely against you. And so her ideas just weren't embraced because she was so different.
But Marie knew she was onto something important.
She had lit upon, almost by accident, an extremely exciting discovery. And as soon as he figured that out, Pierre abandoned his work on crystals and joined her.
To track down their mystery element, Marie and Pierre subjected pitchblende to a battery of chemical procedures.
You break up your rock, you try to dissolve it, you treat it with all kinds of other chemicals.
The goal is to separate the ore into portions with different chemical properties, all the while tracking the radioactive signal.
She then throws away everything that isn't radioactive. It's getting more and more concentrated as she goes through these steps.
The Curies soon discovered that 2 distinct parts of the pitchblende, with different chemical properties, were both radioactive. That meant not one but two new elements might be hidden in the ore.
By July 1898, they were able to announce the discovery of one of those substances with certainty.
Marie, you will have to name it.
The former Mademoiselle Sklodowska thought of her occupied native country, whose very name had been erased from the map of the world.
Could we call it polonium?
Poland, remember, was still not a country. This was one way of putting it on the map.
Eh bien voilà, polonium it is.
Marie next turned her attention to the second mystery element.
She finds the activity is through the roof. It's nearly 1,000 times more active than even her uranium sample had been.
Marie's polonium sample had not been pure enough to yield a unique spectral line. Would this new, more powerful element pass the test?
By 1900, spectroscopy was often seen as the gold standard for identifying the materials you're working with. And if Marie Curie wanted to make some claim that she'd found, in fact, a whole new element, she was going to have to meet the chemists on their own terms. She'd need spectroscopic evidence.
Regardez ici. Il y a une ligne par ici.
Marie's sample showed the presence of the well-known element barium, but it also revealed a pattern of spectral lines never seen before. Strong evidence that she and Pierre had tracked down their mystery element.
She could tell that she had an element that hadn't been seen before, because the spectral lines she got were different.
And in the notebook, Pierre writes in very bold ink the name they decided to give the new element, radium.
But in the 19th century, there had been scores of claims of elements that later proved not to be elements at all. You needed to do more.
To satisfy the chemical community, a spectral line wasn't enough. They had to see the real stuff, which could be weighed, which could be measured.
It was important, as you would with any other element, to isolate this element, to weigh it, and to place it on the periodic table.
So in order to be absolutely certain, she had to have pure material, and that's what she set out to do.
It was my mother who had no fear of throwing herself into that daunting task. Without personnel, without money, without supplies.
To isolate even a speck of radium, Marie would need to process huge quantities of pitchblende, a job too big for her tiny laboratory. The only space available for this work was a drafty old shed, once used as a dissecting room for the school's medical students. As Greer Garson and Walter Pidgeon showed in the 1943 film Madame Curie, the Curies worked tirelessly to separate the radium from tons of pitchblende residue they had shipped from a mine in Bohemia.
Sometimes I had to spend the whole day mixing a boiling mass with a heavy iron rod nearly as big as I was. I would be broken with fatigue by the end of the day. And yet we spent the happiest days of our lives in this miserable old shed. An entirely new field was opening before us.
Marie soon realized that radium was a smaller part of the pitchblende than she ever imagined. Less than 1/1,000,000th of 1%. Isolating it was going to be an enormous job.
Marie's daughter said that had it been up to Pierre, he might not have taken the next step.
The world is done without radium up to now. What does it matter if it isn't isolated for another 100 years?
I can't give it up.
There is a special passion which goes with the discovery of elements, and a line in the spectrum is not enough.
She was after an understanding of nature, and there was very, very little that would stand in her way.
In 1902, after 4 years of arduous work, Marie finally succeeded in isolating 1/10 of a gram of radium chloride from 10 tons of pitchblende residue.
4 years to produce the kind of evidence that chemical science demands.
All of this effort so that she could actually convince the remaining chemists that this was a real, honest-to-goodness element.
She measured radium's atomic weight at 225.9, very close to the current value of 226. And she placed it correctly in the periodic table.
Radium officially existed. The incredulous chemists, and there were still a few, could now only bow before its effects, before the superhuman obstinacy of a woman.
Here she was, still basically a graduate student, and the whole world was beginning to talk about her discoveries. In just these 4 years, she's now discovered 2 brand new elements. Even more important, she's shown that this strange emanation, this radioactivity, is a feature of matter, not specific to one quirky little substance. And she's also developed a quite impressive technique for finding more.
This was the beginning of identifying elements by their radioactive power.
The same technique would soon be used by others to identify more new radioactive elements. In 1903, Marie Skłodowska-Curie became the first female scientist ever awarded a doctorate in France. By then it was clear radioactivity was a pivotal scientific discovery, deserving of recognition.
There's no doubt that Marie Curie had done the lion's share of this work. And yet when the time came to recognize this work, it very nearly went to other people.
A number of prominent French scientists nominated Pierre Curie and Henri Becquerel for the Nobel Prize in 1903. And in this letter, they didn't mention Marie Curie at all.
One of the nominators was Gabriel Lippmann.
It's quite remarkable, since Gabriel Lippmann was her teacher, her mentor. He actually presented her very first paper to the Academy. So he knew about her importance in this work and how central she was to these discoveries. And yet this cabal of Frenchmen just left her off the list. The idea that she could be an important scientist just didn't occur to them. She was totally invisible.
Pierre, and we have to give him total credit for this, turned around and said, I did not conceive of this idea. I helped with the work, but it was someone else's idea that made it possible, and that's Marie Curie.
Pierre was adamant that Marie needed to be included. He immediately wrote back and said, wouldn't it be better, from an artistic point of view, to award the prize to Marie Curie and to me?
In the end, Marie did share in the Nobel with Pierre and Henri Becquerel. She would go on to win a second, all her own. But the real prize was the magical substance for which she would always be known. Some nights the Curies would stop by the laboratory to admire the element Marie called my child.
They arrived in the Rouleau Monde. Pierre put the key in the lock. The door squeaked and admitted them to their world.
Eve Curie, in her biography of her mother,
Don't light the lamps.
describes the wonder of the Curies as they went into their lab one night and saw these glowing vials.
From all sides, we could see gleamings suspended in darkness, like faint fairy lights. Do you remember the day you said to me, I would like radium to be a beautiful color? Radium had something better than a beautiful color. It was spontaneously luminous.
The fact that radium glowed in the dark seemed magical, but it was also troubling because it almost seemed to violate some kind of fundamental physical law.
Scientists had known for some time that light is a form of energy. So if you distill something and it suddenly glows in the dark, you have to ask the question, where does that energy come from?
It's not changing shape, it's not interacting with the environment to get this energy, but it's just glowing infinitely. And we had no idea why it did that.
It was Marie who had the flash of insight. Perhaps some types of matter were changing from one kind to another, their atoms splitting apart and releasing energy in the process.
This theory of the source of the energy is very seductive. It explains radioactivity very well.
But it was an idea many chemists refused to accept.
Tell me, please, how much radium salt is there in the entire Earth? A few grams. On this shaky foundation, they want to overturn our understanding of the nature of matter.
Even the Curies were reluctant to accept it.
The Curies themselves, they wanted to think of elements as immutable, unchangeable parts of nature.
The idea that one could have transmutation from one element to another was very disturbing, even to her. at first.
But the Curie's discoveries inspired others around the world to pursue this daring theory.
The idea that finally got pieced together was that the energy was in fact coming from the disintegration of these atoms themselves. Radioactivity was a sign that the atom itself was unstable. It could break apart.
This discovery implied something even more profound. Up to then, most scientists had believed atoms were the smallest units of matter, solid, unsplittable lumps. But if radioactivity was atoms falling apart, there must be even smaller pieces inside, still awaiting discovery. Thanks to this Polish expatriate, this graduate student, this young mother, scientists hoping to solve the mystery of matter now had a pressing new question to answer. What's inside the atom? In the late 1800s, tubes like this were a staple of the popular science lecture. When electricity was applied to the metal at this end, it would give off a glow that thrilled crowds still mystified by electricity. In 1897, physicist J.J. Thomson of England's Cambridge University set out to find out what these mysterious rays were. When Thomson moved a magnet near a tube modified to reveal the rays, he saw that it bent the path of that beam. Electricity, he realized, must be made up of negatively charged particles, what soon came to be called electrons. But electrons weren't just the unit of electricity. Thomson found that even when he used different metals to generate the rays, the resulting electrons were always the same. His bold conclusion was that the electron must be a tiny piece of every atom, thousands of times smaller than the atom itself.
These things were much, much smaller than anyone had ever thought a kind of physical thing could be. But over time, people began to agree that this was a piece of every atom in the universe, that all of matter had these little parts inside them.
Now the race was on to identify the rest of the atom's pieces and understand how they fit together. This challenge drew many of the best minds in science, including a 22-year-old physicist from one of England's leading scientific families.
My dear mother, 2 letters from you, so here a second from me.
Henry Gwyn Jeffreys Moseley, Harry to his friends, was born with science in his blood. Both his grandfathers had been members of the Royal Society, and his father was a famous naturalist and Oxford professor. But he died when Harry was just 3, leaving him to be raised by his mother, Amabel.
Firstly, the garden. Please occupy yourself in taking many hundreds of rose cuttings. Put them quite close together and ram the earth round them.
Harry and his mother grew very close. Together they laid out a garden alongside their country cottage. And throughout his life, his letters home were filled with instructions.
Such penstemons as the mole killed must be replaced. The quamishes would like to be planted.
As any good gardener, he knew what he wanted planted where, and he told people what to do. He got to be very good at telling people what to do.
I hope the burrowing progresses and that it is all being done with reference to our pretty ground plan.
Moseley earned a degree in physics at Trinity College, Oxford, and then elected to pursue graduate studies 200 miles to the north in smoggy Manchester, whose industrialists had generously endowed the local university.
The laboratory that Moseley came to in 1910 was, at that time, one of the most advanced physical institutes in the world.
But for Moseley, the real attraction was that it was run by the brightest star in physics, an irrepressible New Zealander named Ernest Rutherford. Rutherford had leapt into the study of radioactivity as soon as Marie and Pierre Curie announced their findings. And he had already won the Nobel Prize for his discovery that radioactive atoms give off different kinds of rays and particles as they decay.
So by 1910, he was undoubtedly among the great physical scientists thinking hard about the nature of radioactivity, about how to understand atoms and their parts.
Moseley was soon assigned a research project on radioactivity, and Rutherford kept close tabs on his progress.
Good morning, Moseley.
Well, how's it all going?
He would daily make a round and visit all of the young workers where they were carrying out their experiments.
And the tube is giving off alpha and gamma rays.
They're producing secondary electrons.
Papa, as they called him,
You tried shielding.
would pour out advice, often seeing right to the heart of the matter.
That should do it. That should help.
He was constantly at the elbows and shoulders of his young students, coaxing them on, offering advice on the nitty-gritty of experimental technique. He seemed to have the sort of magic hands to get things to work.
Carry on, word Christian soldiers.
It was a very happy atmosphere in his laboratory because it was like a band of brothers almost.
Rutherford's band of brothers was one of the finest groups of young scientists ever assembled in one place. Among them were Hans Geiger, who would invent the radiation detector known as the Geiger counter, Charles G. Darwin, grandson of the great biologist, and James Chadwick, a future Nobel Prize winner.
He had a very active group of young researchers who were wondering about ultimate questions of what's the nature of matter, with new discoveries practically every week.
One of the most exciting discoveries came just a few months after Moseley's arrival, as Rutherford's team continued to probe the structure of the atom. They knew that J.J. Thomson's tiny, negatively charged electron was one piece of the puzzle, but that left two big unanswered questions.
Since atoms are generally neutral, that meant that the atom itself had to somehow have a positive charge to balance the negative charge out.
But where in the atom were the positive charges needed to offset those negative electrons?
And a related question, since people knew by this point the electrons were so much less massive than the atoms themselves, where was the mass distributed?
Rutherford and his students had been trying to answer these questions with the help of the positively charged alpha particles that poured out of radium during radioactive decay. They aimed a beam of alpha particles at an ultra-thin sheet of gold foil.
Most of the time, these alpha particles would sail right through. But every now and then, some of these projectiles would actually bounce practically right back in their faces. And that was really, really unexpected.
It was the most incredible thing that has ever happened to me. It was almost as if you had fired a 15-inch shell at a piece of tissue paper, and it came back and hit you.
In late 1910, Rutherford came into the lab one day and announced he knew what this surprising result meant.
It meant that the atom must be mostly empty space, but have some incredibly dense, hard center.
If the atom's positive charge and most of its mass were concentrated in a tiny central core, it would let most particles sail through, but repel any positive charge that came near the center.
Then you can give the incoming alpha particle a real kick, and sometimes turn it all the way around.
So with that, we had this really quite brand new vision of the structure of the atom. Almost all of its mass was concentrated very, very tightly in a minute little space in what we would now call the nucleus, and then separated by mostly nothing. You have these negatively charged electrons that sort of whizzing around, but at a great, great distance on the scale of the atom.
One of the most remarkable things about the atom is that it's mostly made of nothing.
I think the feeling in those hallways, the laboratories of Manchester, was one of great excitement. They could sense that Rutherford and his team had literally cracked open a new view of matter.
But while all this was going on around him, Moseley was consigned to plugging away on radioactivity research projects.
I'm repeating someone else's experiment to please Rutherford, so the work is not very exciting. I'm hoping to be through with it soon.
From his correspondence, I think he found it actually slightly mundane just to be following on behind other people and not really making his own distinctive mark.
So in the spring of 1912, when a piece of his radioactivity equipment broke, Moseley seized the opportunity to strike out in a new direction.
My dear mother, I'm sorry that I didn't answer your letter sooner, but I was very busy. Last Thursday, we got the result we were searching for, using the X-rays.
Moseley had turned his attention to some exciting news out of Germany. X-rays, the same rays that had so captivated the world 15 years earlier, had been found to have properties like those of light. Ever since Newton, it had been known that a prism could split light into a series of distinct colors, each with its own wavelength or frequency. What the German scientists had discovered was that X-rays could be split up, or diffracted, in the same way, with the help of a crystal. Only the resulting image was not a rainbow, but a symmetrical pattern of spots on a photographic plate.
Power on. 15 volts and steady.
Intrigued, Moseley asked Charles G. Darwin to join him in investigating this curious X-ray pattern.
220 degrees, 10 minutes.
Darwin was actually a mathematician, and that's really why Moseley got hold of his services, because he knew that this was going to imply some complex mathematics.
Moseley and Darwin concluded that the atoms inside the crystal were neatly arrayed in rows that reflected the X-rays to create the pattern of spots. Excited by this discovery, Moseley and Darwin asked Rutherford for permission to devote all their time to this new project.
I don't really think that we are equipped. We don't really have the supervision for this sort of thing.
Rutherford, who knew nothing about X-rays, was not very enthusiastic about this new departure, so he at first opposed it.
Are you absolutely sure this is something you want to do?
We were fired by our interest in this unexplored field. Had no idea where it would lead. At the time, X-rays were still mysterious. We simply wanted to know what they really were. Finally, we persuaded him to let us try.
Okay, well, on the condition that if you run into trouble of any kind, you do...
I think it was essentially their enthusiasm for the subject which convinced Rutherford that, yeah, this was worth a shot.
And keep me informed
Certainly.
all along the way, okay?
Certainly, sir.
Okay.
For 6 months, the two young researchers holed up in the laboratory.
220 degrees, 20 minutes.
15 volts and steady. I wish I were with you to see all the fresh spring, but here it's all work. I'm like a gnome after a long winter of darkness, longing for some light.
Working with Moseley is one of the most strenuous things I've ever done. He is, without exception, the hardest worker I've ever known.
I'd arrive at the laboratory in the morning and meet Moseley just as he was leaving. He'd been at it all through the night. 15 straight hours.
Indeed, one of Moseley's skills was knowing where in Manchester you could get a meal at 3 in the morning.
We've sent a letter off to nature, describing what we have found so far. But we must keep on with the work. Many others are on the same track.
Moseley was not alone in realizing this was exciting. There was some pretty steep competition, like William Bragg and his son William Lawrence Bragg were already working hard and fast on similar techniques.
Aware of this competition and anxious to return to Rutherford's work on the atom,
Thought I'd come by to bid you farewell.
Darwin decided to leave the partnership in the summer of 1913.
I suppose this makes sense. You're always a better theoretician than you are a lab tinkerer.
Will you go on alone?
Oh, certainly. I think this might lead to something.
Rather than abandoning the work,
I wish you all the best.
Moseley changed his approach, leaving basic research on X-rays to others.
Moseley says, well, okay, I'm not quite sure what these things are, but I know perfectly well how to use them.
Having done the basic work with Darwin, he decided to use the method as a tool to investigate the nature of the elements.
And that is when his brilliant discoveries began.
Moseley set out to learn if each element had a unique X-ray spectrum, a barcode like the ones that had been discovered a half-century earlier using light. To find out, he placed a sample of an element inside an X-ray tube. When a beam of electrons struck the sample, the element gave off X-rays. Moseley could then determine the element's X-ray spectrum.
The whole subject of X-rays is opening up wonderfully. When we fire electrons at a target made of platinum, we get a sharp line spectrum of 5 wavelengths. Tomorrow, I will search for the X-ray spectra of other elements. I believe they will prove much more important and fundamental than the ordinary light spectra.
While the light spectra had been invaluable in identifying new elements, they hadn't solved certain puzzles about the ordering of the elements in the periodic table. The elements were arranged in columns with similar chemical properties, but they also tended to fall in order of increasing atomic weight, the amount a single atom of an element weighed.
But it's not perfect. Every now and then, there seem to be anomalies, little reversals, where chemical properties seem to suggest one kind of ordering, but their weights suggested the opposite order.
For example, there was cobalt and nickel. Chemically speaking, cobalt should occur before nickel, and yet its weight is higher, and nobody knew why these inversions were happening.
To find out if X-rays could solve this riddle, Moseley set out to test 10 neighboring elements in the periodic table, including that troublesome pair, cobalt and nickel. But Moseley quickly realized he had a problem. For each element he tested, he had to use the lab's vacuum pump to empty the tube of air.
Vacuum pumps were jealously guarded devices. Lots of people in the lab needed a vacuum to do their research, and you had to join the queue. But Moseley realized that if he could put lots of these little elements at once in the same tube, then he could really make progress.
So he designed a long X-ray tube and built a tiny railroad car to carry his samples along inside it.
And tied a little piece of silk fishing line to them, and then tied that line to a little bobbin.
By turning the bobbin, Moseley could bring his samples, one after the other, into the line of fire.
And so he could do all of these elements in one go, if you like, with the same vacuum tube.
As each metal was struck by the electron beam, it gave off X-rays. When diffracted by a crystal, they created a series of lines on a strip of film.
I've worked out a simple way of finding the wavelengths of my different elements.
Once he got it up and running, he said it's so easy, it's almost a sin to snatch the bread from those hungry Germans.
In 5 minutes, I can get a strong, sharp photograph of the X-ray spectrum.
Moseley found, just as he had hoped, that each element had a unique X-ray spectrum.
In just 4 days, I've got the spectrum of chromium, manganese, iron, cobalt, nickel, and copper. There is here a whole new branch of spectroscopy.
But not even Moseley expected what he found when he compared the spectra of all 10 elements in his series.
The result of these measurements was absolutely extraordinary.
He decided simply to take his photographic film and to arrange the film according to its frequency.
Each piece of film represented a different element in his series.
The frequencies of the X-rays that came out had an amazingly simple relationship.
As he laid them out, one after the other, Moseley found that their dominant X-ray lines rose in frequency, step by step.
And that produces this beautiful staircase.
He had no idea when he started to measure these frequencies that the result, now known as Moseley's staircase, would come about. That was a great surprise.
I think he must have been astonished. And I think the scientific world was astonished that it was that simple.
It would be years before scientists understood the reason for this striking pattern. But Moseley knew at once he had made a fundamental discovery.
He thought, now I have a means for the first time to really tell which element is which and to put them in a proper order.
Moseley's X-ray lines showed that cobalt and nickel were just where they should be, even though their atomic weights were out of order. The conclusion was inescapable. The X-ray spectra of the elements didn't depend on their atomic weights, but on something even simpler.
There was a remarkably simple relationship between the wavelength or the frequency of that X-ray that came out and something they came to call the atomic number of the element.
Up to now, atomic number had simply referred to the number of an element's box in the periodic table.
All the way back to Mendeleev. It's where in the row you are. It's counting one by one.
But Moseley's results showed atomic number was much more than a convenient label.
What we have here is proof that there's a fundamental quantity in the atom which increases by regular steps as we pass from one element to the next. This fundamental quantity can only be the charge on the central positive nucleus.
Moseley had discovered that the nucleus was not one big positive blob, but a collection of positively charged particles that increased in number with each heavier element. Building on Moseley's work, Rutherford would soon discover this next piece of the atom, the proton, and show that each element in the periodic table is defined by the number of protons in its nucleus, its atomic number.
Our experiments show that the atomic number always increases by a single unit from element to element. For hydrogen, the atomic number is 1. For helium, 2. For lithium, 3, and so on.
Moseley's discovery put the periodic table in a whole new light. For the most part, elements were arranged in increasing atomic weight.
But that's not the real reason for that tremendous order that we find among all the elements. It really is marching along atomic number, the amount of positive electric charge on that nucleus, none of which was known in Mendeleev's own day.
Weights didn't matter. Something fundamental that was deeper in the atom was what mattered.
Moseley's proof that the properties of an element are determined by its atomic number, not its atomic weight, ranks in importance with the discovery of the periodic law itself. In some respects, it's even more fundamental.
Moseley and atomic number, that's really the crucial moment where we find out what an element really is.
Ethereum, beryllium.
Armed with his X-ray machine, Moseley could quickly sort through the dozens of supposed new elements chemists had claimed to have found, separating the real from the imagined.
You could just distinguish between types of matter with a brand new technique, not dependent on their chemical properties, but by measuring the atomic number based on these X-rays.
Moseley's X-rays allowed him not only to rule out elements that didn't exist, but also to predict what new elements would eventually be found. In 1914, Moseley measured the X-ray spectra of 30 additional elements beyond the first 10. They too fell into line according to atomic number, clearly revealing where elements were missing and where no new ones could fit. For the first time, one scientist marveled,
40, 41.
It was possible to call the roll of the chemical elements,
43.
To determine how many there were and how many remained to be discovered.
The idea that somebody could know how many elements God created, but that was terrific.
After Moseley's work, it was clear that there were 7 and only 7 elements remaining to be discovered.
But since we can now predict the X-ray spectra of these elements, they should not be difficult to find.
In 1914, Moseley's continuing work on the elements was interrupted when his country called.
My dearest mother, I am now a second lieutenant in the Royal Engineers.
England had been drawn into war by events in Europe. Like many others of his generation, Moseley felt a duty to serve.
I was very lucky to get into the army so quickly because RE commissions are much in demand.
He had a bit of difficulty actually getting into the army because he wasn't an engineer and the Royal Engineers wanted engineers.
He badgered the recruiting officers to allow him in.
By the summer of 1915, Moseley was stationed in Turkey.
It gets hotter here by the day, and only cool nights and sea bathing keep life tolerable.
I had mixed feelings about the enlistment of so many young men of science. Pride over their ready response to the country's call. Apprehension about irreparable losses to science.
On August 3rd, 1915, he wrote from Gallipoli.
My insides return to duty and let me once more enjoy the good things which are sent us. Foremost among them, your Tiptree jam.
One week later, as they attempted to take a ridge, Moseley's brigade was overwhelmed by Turkish troops. The 27-year-old communications officer was shot in the head and killed.
The news of Moseley's death was a terrible shock at Manchester because by that time it was already clear that Moseley was one of the most brilliant young physicists of his generation.
In the scientific community, there was a big sense of outrage, particularly from Rutherford, because he did feel Moseley was someone special.
The services he could have performed for his country. Instead, they exposed him to the chances of a Turkish bullet.
Tributes poured in from around the world, none more moving than that of American physicist Robert Millikan, who had met Moseley during a visit to Rutherford's lab.
He threw open the windows through which we can glimpse the subatomic world with a clarity never dreamt of before. 27 years old. If the European war had done nothing worse than snuff out this one young life, that alone would make it one of the most hideous crimes in history.
In the decades after Harry Moseley's death, chemists found all the missing elements he had left room for. By 1945, every space was filled, from the lightest element, hydrogen, to the heaviest, uranium. The periodic table was complete, except it wasn't. By this time, the next generation of element hunters had already begun a whole new chapter. They had figured out how to create new elements, elements that didn't exist anywhere on Earth. The central character in these events was a young American chemist named Glenn Seaborg. He set out with a simple desire to make one of these new elements, but he would end up changing the world forever, unleashing a force of unimaginable destructive power. The story begins in late January 1939, when a young physicist in Berkeley, California, learned of a startling discovery in an unusual way.
One of my father's colleagues, Louis Alvarez, was sitting in the barber shop getting his haircut when he read about this in the paper.
Buried on an inside page of the San Francisco Chronicle was a story from Washington. German chemists had split the uranium atom by bombarding it with neutrons. I stopped the barber mid-snip and ran all the way to the radiation laboratory to spread the word. The first person I saw was my graduate student, Phil Abelson.
I was at the control console operating the cyclotron. About 9:30 a.m., I heard the sound of running footsteps outside.
Phil! The Germans have split the uranium atom. Honest Trussmen have done it. Uranium split in two. Joey!
When I heard what he had read, I was stunned.
Word spread quickly across the University of California campus. One of the first to hear the news was Glenn Seaborg, then a 26-year-old chemistry instructor.
He was just stunned, and he spent hours walking the streets of Berkeley thinking about it.
I was exhilarated at the discovery, but at the same time, I felt stupid for having overlooked this possibility. I'd missed a chance for an astounding discovery.
Many others had missed it too. In fact, the splitting of the atom, nuclear fission, was so unexpected that it forced scientists to rethink what they knew about the atom. To understand why, we need to step back a few years to 1932, when another of Rutherford's boys, James Chadwick, discovered the final piece of the atom, the neutron. The neutron has almost the same mass as the proton, and they both occupy the nucleus, but the neutron is electrically neutral, hence its name. Right away, scientists realized this made the neutron the perfect projectile for firing at the atom. Unlike those positive alpha particles that Rutherford and his students had been using, it would not be repelled as it approached the nucleus. It could go right in.
You didn't have to fight the electrical repulsion to get this object to go inside the nucleus and probe the structure there.
One of the first to use the neutron in this way was an Italian physicist named Enrico Fermi. In 1934, Fermi began firing neutrons at uranium atoms, creating a shower of fragments he would then analyze. He found that a neutron sometimes chipped off a piece of the uranium nucleus, lowering its atomic number and turning it into a different element, a few spots lower in the periodic table. But some of Fermi's fragments didn't match any of the elements just below uranium. What could they be? Fermi concluded that sometimes an incoming neutron is absorbed by the uranium nucleus, and then spontaneously changes.
The neutron becomes a shapeshifter and changes itself into a proton. But when you change the number of protons in the atom, you change the chemistry, you have changed the identity of the atom.
They eventually concluded, they published a paper saying they had found transuranic elements, elements that were even heavier than uranium. They figured they had pushed beyond the end of the periodic table.
For this remarkable achievement, Fermi won the Nobel Prize in December 1938. But even as he was shaking the hand of the King of Sweden, German scientists were making the discovery that would prove Fermi wrong. Like almost everyone else at the time, Fermi had underestimated the neutron.
It was very much smaller than the nucleus it was being fired at. It had no electric charge. It couldn't shove things around by electric repulsion.
So Fermi's team hadn't checked to see if the neutron had broken the uranium nucleus in half into much lighter elements.
They figured there's no way this tiny little wimpy thing could bust apart something as huge, as massive as an entire uranium nucleus.
Breaking a nucleus in two with a neutron would be like breaking a boulder in half by tossing a pebble at it. We all knew it was impossible for uranium atoms to break apart in that way.
But when the Germans repeated Fermi's experiments, they found that's exactly what happened.
They did not find things that looked heavier than uranium. They found well-known elements that were about half as heavy, much, much lower on the periodic table. The uranium nucleus had been split in two in a way that no one had imagined possible or even worth looking for.
The tremendous energy released when the atom split had profound implications for a world at the brink of war.
Across the world, physicists came to remarkably similar conclusions right away. Could the energy trapped in that nucleus be used to make an explosive, unthinkably more powerful than conventional chemical explosives?
A lot of people were thinking about the possibility of the atomic bomb. But my father, he was mostly thinking about the scientific implications.
For Seaborg, the discovery of fission presented an unexpected opportunity, a second chance to be the first to discover elements beyond uranium.
Fermi had said he discovered all these transuranium elements. Those findings just went out the window, so if there were transuranium elements to be found, well, they were still there to be discovered.
And Berkeley was the perfect place to do it. Under the leadership of Ernest Lawrence, Cal's radiation laboratory had led the world in the development of the cyclotron, a device for flinging subatomic particles at ever greater speeds.
What Lawrence did was figure out you could take a proton or some particle that you're accelerating and put it in a circular path using magnetic fields to make it go in a circle.
By rapidly switching the electrical charge of the two Ds, Lawrence kept the proton chasing the ever-moving negative plate, boosting its speed on each pass.
You hit it once, it comes around again, you hit it again, you hit it again, you hit it again, and then suddenly you've got this really energetic, tiny particle that you can then aim at your target and use it to study what's going on.
Just weeks after the news of fission broke, a young Berkeley physicist named Ed McMillan set out to study this new phenomenon. He would repeat the Germans' experiments by bombarding uranium atoms with neutrons from the cyclotron. To prepare his target, he applied a thin layer of uranium oxide to a piece of filter paper. His goal was to split the uranium atoms and track how far the resulting fragments flew.
Ed started by capturing the fission products in a stack of thin foils. But eventually, he found that cigarette papers worked just as well.
He stacked the cigarette papers behind the uranium-coated filter paper. When this target was struck with neutrons from the cyclotron, atomic fragments would scatter in all directions. Some would burrow into the stack of cigarette papers, penetrating to different depths. McMillan then checked the papers one at a time to see how far the radioactive fragments had traveled. As expected, he found different levels of radioactivity on each paper. The surprise came when he measured the target itself. It was much more radioactive than expected, suggesting that one product of the reaction hadn't moved at all, but remained on the filter paper.
And this lack of mobility implied that it might not be a fission product at all.
As the possibilities raced through Macmillan's mind, he quickly arrived at an explanation. This fragment had stayed put because it was much heavier than the others. Instead of splitting into smaller pieces, a uranium atom had absorbed an incoming neutron, and then that neutron had spontaneously changed into a proton, in just the way Fermi had proposed.
What Macmillan was seeing was what Fermi thought he was seeing.
If so, this would be a brand new form of matter, the real element 93. But to prove it, he would need to show that its chemistry was unlike any other element, a precaution Fermi hadn't taken. For help on this, Macmillan turned to an old friend, Phil Abelson, who was back in Berkeley on a short vacation.
Phil Abelson was really taken by this activity Macmillan had found, and he decided he was going to follow up on it. It was certainly a very productive vacation because it didn't take him long, really a few days, to rule out that it was any of the other elements 92 and down.
We had discovered element 93.
They named it Neptunium because it was beyond uranium, just as the planet Neptune is beyond Uranus. With this discovery, the search for elements had entered a whole new realm. Up to now, it had been a matter of finding elements that already existed in nature. But from this point on, element hunters would be creating new elements. There was no telling how far the periodic table might extend. Macmillan immediately set out to create element 94.
While Ed was doing this research, he lived at the faculty club just down the hall from me. I kept track of his progress at breakfast, in the hallway, even in the shower.
My father was fascinated by Macmillan's search for 94, and he knew that Macmillan was closing in on it, and then suddenly Macmillan disappeared.
Like many other American scientists, Macmillan had been called to help the country prepare for war. He had moved to the Massachusetts Institute of Technology to join the team developing radar.
So my father wrote to him and asked him if he could continue with this project looking for 94 as a collaborator. And Ed Macmillan very graciously said, yes, I'd be delighted if you would do so.
If Ed had left for MIT just a few months later, he certainly would have been the one to find element 94. As it was, I was in the right place at the right time. It would be the discovery that changed everything for me.
As a chemist, Seaborg was thrilled at the chance to create a new element. But he conducted his research with one eye on the changes that were sweeping the world. In the past year, Germany had invaded Poland. France and Great Britain had declared war. Italy had sided with Germany. Fighting now raged across much of Europe and North Africa. Albert Einstein, alarmed at these events and aware of Germany's head start in nuclear research, had written to President Roosevelt, urging him to launch an American effort to create an atomic bomb, powered by the fission of uranium. By now, it was clear there are two very different kinds of uranium. Only one of them was easy to split.
The one that would do that most readily was a very unusual kind of uranium that had fewer neutrons in the nucleus, this very fissionable, potentially explosive kind of U-235.
But that's only about 1% of all the uranium. The much more common element is the uranium-238, but it doesn't fission.
But Seaborg realized he might be able to turn this inactive uranium into a new element that was capable of splitting.
We knew early on that element 94 could be a big prize. If we could transform U-238 into a fissionable material, we would increase 100-fold the amount of material usable for a bomb.
With this goal in mind, Seaborg picked up where Macmillan had left off. He knew from Macmillan's work that uranium bombarded with neutrons sometimes changed into neptunium. But neptunium itself was radioactive, spontaneously changing form. Could it be shape-shifting into element 94? To find out, Seaborg and graduate student Arthur Wall used the Berkeley cyclotron to create a sample of neptunium, in the same way Macmillan had.
Arthur, what we want here is the sample directly in line. You see?
They would then watch for signs that neutrons inside it were changing into protons, forming element 94. Sure enough, a special radiation detector showed that's exactly what was happening. But to be sure they had a new element, they'd need to create enough of it to test its chemistry. For that, they'd have to wait for neptunium to break down, atom by atom, into what they hoped was element 94. After a month, Seaborg and Wall had enough material to test. Mindful of Fermi's mistake, they painstakingly checked to make sure the product of their experiment was not an element that had already been discovered.
It took them weeks to actually separate it from every other known element, but they were eventually successful in doing that.
The last possibility was finally eliminated late one night in February 1941. There was then no doubt. They had discovered element 94, plutonium.
We felt like shouting our discovery from the rooftops. Under normal circumstances, we would have rushed to publish our claim to the discovery of a new element.
But they realized that if this was a fissionable element, it was of military importance and there was a war going on, and so they actually had to keep it secret.
Maybe for the first time ever in the history of this race to find and create new elements, Seaborg was not able to just tell anyone he knew about this very exciting new discovery. What had changed was the condition of the world.
By now, German planes were regularly bombing English cities. Japan had entered the war. And there were reports that Adolf Hitler had launched an effort to create an atomic bomb. In response to Einstein's plea, President Roosevelt had authorized a modest research program into the possibility of a weapon fueled by the fission of uranium-235.
And Seaborg realized here's a type of material he'd made from scratch in the laboratory that might be an even more efficient fuel for that kind of weapon.
But was it? Discovering plutonium was just the first step. Seaborg would need to create much more of it to find out if this new element was capable of fission. Joining Seaborg to answer this critical question was Emilio Segre, a Jewish physicist who had fled Italy amidst rising anti-Semitism.
I hope he's paying attention to Mussolini's.
They placed a 2.5-pound sample of uranium next to the cyclotron and bombarded it with neutrons.
During the early work on the discovery of plutonium, they were working with very small amounts, so they were not concerned about radioactivity. But to test for the fissile nature, they had to use much larger quantities, and that meant that they had to worry about radiation exposure. They were not really set up to do that kind of work. They had to just improvise, so they would have goggles, they would have lead-lined gloves. They ended up using buckets on poles. On looking back, my father said, gee, you know, it really seemed primitive, although they managed to do it.
Seaborg and Segre separated element 93 from the rest of the reaction products, spun it to further purify the sample, and then did it all over again.
We called it a night at 10 p.m., but we were back first thing in the morning to repeat the process. 6 cycles over the next 3 days. It was tedious work, but the hours flew by because we knew we were on the verge of a discovery.
The work was finally completed in March 1941.
The results of all these separations was a very small amount of plutonium that they put on a small dish, and they actually covered it with Duco cement so that it wouldn't go anywhere.
They labeled it Sample A.
Then came the moment of truth. Was this new element fissile? Was it a potential source of immense power? We placed Sample A in the path of the cyclotron's neutrons. Okay, Joe. And had our answer almost immediately. The counter registered the unmistakable kicks of fission.
They knew immediately what the implications were. There was a large portion of uranium that could not be used in a bomb. What plutonium offered was a chance to turn all of that uranium-238 into a fissionable material.
Seaborg figured out how to take this uranium-238 and turn it into a new element, plutonium, which readily fissions.
And that meant there could be much more material made for bombs or for use in nuclear power.
Seaborg's discovery soon came to the attention of the leaders of the nascent American effort to create an atomic bomb, including physicist Arthur Compton and Harvard President James Bryant Conant, who met in late 1941 to discuss Seaborg's findings.
That lunch where they discussed the possibilities of creating a bomb was on December 6th, 1941. The next day, my father was home at the faculty club listening to a football game on the radio when the announcer broke in.
We interrupt this program to bring you a special news bulletin. The Japanese have attacked Pearl Harbor, Hawaii by air. President Roosevelt has just announced.
Our team had already been working hard in anticipation of war. In an instant, the day that shall live in infamy made work on anything else seem irrelevant.
The American people in their righteous might will win through to absolute victory.
With America now in the war, the atom bomb effort took on a new urgency. The leaders of the effort asked Seaborg to report to the University of Chicago, where he would spend the next 4 years working on the Manhattan Project. Newly married and just 30 years old, he was put in charge of a team responsible for separating plutonium from other fission products. The responsibility for creating the plutonium fell to Enrico Fermi, who had fled fascist Italy after winning the Nobel Prize. In an abandoned squash court under the university football stands, Fermi's team built a nuclear reactor out of wood, graphite, and uranium. In a historic experiment in December 1942, Chicago Pile 1 went critical, spitting out energy and neutrons at an ever-rising rate.
Their first ever nuclear reactor was actually creating a self-sustaining nuclear reaction. Certain nuclei would split in two, that would release some neutrons as well as energy.
Those neutrons then collide with other atoms, and then you get a cascade, which we call a chain reaction.
Fermi's chain reaction not only showed an atomic bomb was possible, but also provided a more efficient way to turn uranium-238 into plutonium. From Fermi's experiment emerged two distinct strategies for making an atomic bomb. One would seek to concentrate the tiny amount of natural uranium that could be split. The other would focus on making plutonium.
Our challenge was to find a way to separate relatively small amounts of plutonium from tons of material so intensely radioactive that no one could come near it.
As the magnitude of the challenge became clear, Seaborg would recruit more than 100 chemists to join him in the effort.
No matter what you do with the rest of your life, I said, nothing will be as important as your work on this project. It will change the world.
In 1943, banking on the process Seaborg's team had developed, the U.S. government began building a huge separation plant in Hanford, Washington. Here, in buildings as long as 3 football fields, plutonium would be made by remote control.
When my father got out there, he was just awestruck, and he couldn't believe that this element that he had discovered would result in these huge plants being built.
From Hanford came the pounds of plutonium that were needed for a bomb. On July 16, 1945, at a desert site near Alamogordo, New Mexico, scientists from nearby Los Alamos conducted the first test of an atomic bomb with a weapon made from plutonium. A blinding flash of light and a deafening explosion signaled the beginning of the nuclear age. Just 3 weeks later, an American bomber dropped a uranium bomb on the city of Hiroshima, killing 100,000 Japanese. 3 days after that, a plutonium bomb destroyed the city of Nagasaki, finally bringing the war to an end. Only then could Seaborg reveal the discovery that had made this bomb possible. For their discovery of the first two elements beyond uranium, Ed McMillan and Glenn Seaborg won the Nobel Prize in Chemistry. But Seaborg wasn't content to rest on his laurels.
Seaborg had the ambition to create more new elements, go beyond element 94, beyond plutonium.
So even before the war ended, he and his Chicago team had resumed the hunt for new elements.
Thank you, Bob Murphy, and good evening, everyone. Well,
Late in 1945, my father was on a radio program called The Quiz
our most
Kids.
distinguished scientist, Dr. Glenn T. Seaborg.
And one of the kids asked him, as kids do, have you found any new elements lately?
Oh, yes, Dick. Recently, there have been two new elements discovered, elements with atomic number 95 and 96.
And that's how the world came to know about americium and curium.
Back at Berkeley after the war, Seaborg and his team continued their quest, bombarding heavy elements with smaller ones in hopes they would fuse to form a brand new type of matter. They created 5 new elements in the next 10 years, including berkelium and californium, and rearranged the periodic table in the process. Since Seaborg and McMillan first ventured beyond uranium, more than 25 new entries have been added to the table, including elements named for Lorentz, Mendeleev, Fermi, Einstein, Curie, Rutherford, and Seaborg himself. Around the world today, others continue to hunt for new elements using techniques like those Seaborg pioneered. So far, there are 118 known elements, each with its own distinct personality. And yet, all these elements, and any new ones we might find, are made up of just a few things in combination. Not air, water, earth, and fire, as the ancient Greeks believed, but protons, neutrons, and electrons. Amazingly, all of matter, planets and stars, plants and animals, you and me, it's all made of just these 3 basic parts: protons, neutrons, and electrons, mixed in different ratios. We know all of this because of a long chain of people who've struggled to answer the simple question, what is the world made of?
We're surrounded by matter. It's everything that we see and interact with. And yet, at the time this quest began, nobody understood what it was made of. Nobody understood anything about it.
Just making one tiny step in the understanding of the natural world sometimes takes generations. There's no guidebook to tell us how to do this. We have to figure it out.
Nature is wonderful and mysterious, and it's hidden. But if you apply the tools of science, you can make it reveal its secrets.
It's taken centuries just to identify the elements, with each generation of scientists building on the work of those who came before. But this is just the first step. Still to be answered are myriad questions about how these building blocks fit together to make the infinite variety of substances in nature, and how we can combine them in novel ways to make fantastic new materials nature never imagined. Answering those questions will take the efforts of many more scientific detectives like the ones we've met. As much as we've learned in the search for the elements, we've only begun to solve the mystery of matter.
Major funding for the Mystery of Matter Search for the Elements was provided by the National Science Foundation, where discoveries begin. Additional funding provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education, and by the following. To learn more about the search for the elements and watch bonus videos on the featured scientists, visit pbs.org/Mystery of Matter. The Mystery of Matter Search for the Elements is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS.